In the previous module 8.1, we had given a complete derivation of the Kalman filter where the dynamics is linear and the observations are linear functions of state. This is the classical LQG problem. We gave a complete derivation of the Kalman filter equations and we illustrated profusely with a scalar example. We talked about the evolution of model forecast without observation. Then we brought an observation, we did the Kalman filter derivation. We also analyzed the properties of the growth rate of forecast errors and examined under what condition the forecast errors will converge. And then we also talked about stability of the filter in terms of what happens to the errors in the stability of the filter. You can readily see this analysis provides a complete characterization of the behavior of Kalman filter equation, the classical Kalman filter. So when we say Kalman filter, we essentially mean application of the filtering equations in the case of linear dynamics and linear observations linear in this state. So that is the classical LQG. Now in the early days when Kalman filter was implemented, especially one of the earliest application was in space travel, the onboard computers had only 8-bit, they had only 8-bit processors. So when you do arithmetic in 8-bit processors, that could be errors due to round off. One way to be able to improve the quality of computation is to be able to reduce the conditioning numbers for matrices that are involved. One way to reduce the condition number for matrices is to consider square root versions of the matrices instead of the matrix themselves. So what kind of matrices we are involved in? We are involved in forecast covariance, analysis covariance. These matrices, if it happens to be a large condition number, there could be difficulties coming from numerical instabilities. So in order to be able to induce numerical stability in the early to mid 60s, it was felt that one needs to be able to improve the conditioning of the calculations in order to improve the overall stability and accuracy of the solutions calculated. That led to what is called square root filters. Since we have derived the Kalman filter equation within the covariance setup, it is called covariance square root filter. I also want to remind you the inverse of the covariance is called information. So one could readily derive the Kalman filter equation in the information form, or that is called information filter. Once in other words, instead of working with the covariance, we will simply work with the inverse of the covariance. While if the covariance is symmetric positive definite, its inverse is also symmetric positive definite. So both the covariance and its inverse, namely the information matrix, all have positive square root. So we have covariance square root, information square root. These are some of the different versions in which Kalman filter equations can be readily and easily written. The square root versions in general have better stability properties, and we are going to give an argument how to derive the Kalman filter equations within the framework of covariance square root filters. So that is the aim of this module. There is also another motivating aim. Sooner we will go into what is called nonlinear filters. Nonlinear filters are very, very difficult problems to solve. We can only approximate. In the case of nonlinear filters, we will also introduce an approximation, one form of approximation using what is called ensemble filters. There is a natural connection between ensemble realizations of filters with covariance square root filter. So it is also for that reason we would like to educate the reader with respect to the derivation of the Kalman filter equations not in the covariance form but in the square root of the covariance form. So that leads to covariance square root filter. Please recall, square root of a symmetric positive definite matrix A can be given in one of three ways. One is using Cholesky, another is using a symmetric square root version and solving the symmetric square root version using a Newton's method. Another one is called the eigenvalue decomposition. For simplicity in calculation, to illustrate basic ideas, we would either use Cholesky or eigen decomposition, whichever is convenient for discussion. In this particular case, we are going to be dependent on the eigenvalue, eigen decomposition based square root version. Please go back to the previous case. X bar is a matrix. So this is X bar times this. So this could be written as this is going to be written as X bar times X bar transpose, that X bar matrix X bar. So this must be actually X bar is equal to X times lambda to the power half. Lambda to the power half is the square root of the diagonal matrix that consists of eigenvalues. Since the matrix A is positive definite, all the eigenvalues are positive, square root exists. So this is how the matrix square root is defined. So we are going to use the matrix square root derived from eigen decomposition in our discussion of the covariance square root filter derivation. So let me quickly talk about the covariance matrix and the properties. If A is a matrix, AXI is equal to lambda I, lambda A is SPD, so all the eigenvalues are positive. So this can be written succinctly as A x1 xn, x1 xn x2 to diagonal. So that becomes this. The matrix X is such that it is orthogonal. Therefore, by exploiting this property, I can get a multiplicative decomposition. Lambda is lambda to the power half, lambda to the power half. So I can get a decomposition which is X bar, this is that, and that is also equal to in component form lambda I times xi transpose. So this is the crux of the eigen decomposition. This is the crux of the eigen decomposition. Now what are we going to do? We are going to talk about two things, full rank as well as reduced rank formulation. What do you mean by full rank reduced rank formulation? If I took all the eigenvalues and eigenvectors in the sum, that is called the full rank. So this is the full rank factorization. Now in here we are going to assume all the eigenvalues 1 to r are large, from r plus 1 to n are small, it can also be shown that the trace of the matrix A, which is a covariance matrix. So if A is a covariance matrix, A is SPD, trace of A is equal to sum of all the eigenvalues, I is equal to 1 to n. So I can divide this into into a summation of two parts. I1 is equal to r lambda I plus summation lambda I is equal to I is equal to r plus 1 to n. If this is small compared to this, approximate this by I is equal to 1 to r lambda I. Therefore, I am going to take only the first r columns corresponding to the first r eigenvalues. So this is the matrix of first r eigenvalues where r is a number which is less than or equal to 1, 1 is less than or equal to r. So r lies in this region. If r lies in this region, now I can approximate A using the product of X bar and X bar transpose. Please understand the rank of this matrix is R. So this is what is called rank R approximation to A. rank R approximation to A. Why are we talking about rank R approximation? Because it also comes from the computational demands. If the matrix is very large and if the eigenvalues are such that 1 to k up to n, if the eigenvalues falls very sharply like this, it can be shown that the sum of the eigenvalues, the sum of the first R eigenvalues, that means the sum of the first R eigenvalues I is equal to R 1 to R divided by sum of I is equal to 1 to n lambda I, which is the this is the total sum versus partial sum, if this is greater than or equal to 90%, let us say. That means 90% of the information are contained in the first R eigenvalues, or it could be 95%. 95% of the information are contained in the first R values. So the value of R will depend on the kind of percentage you are interested in, the kind of approximations you are willing to accept. So if I consider the full rank, I will have 100% of the variance accounted for. If I am going to go for a reduced rank, I am going to neglect eigenvectors corresponding to very small values of very small eigenvalues. So we can we can talk about rank R approximation. So in this case xi transpose is a rank 1 matrix. A sum of R rank 1 matrices gives you a rank R approximation. Now please realize these eigenvectors to start with, they are all linearly independent. So the first subset of R are also linearly independent. So these are all the choices one has in terms of approximation. So we talk about two things now. I want to go back to where we are. We started with the A positive definite matrix. We got an eigen decomposition. We also got a square root version of A. A is equal to x bar times x bar transpose. That is the square root. Now we are trying to interpose another idea. If in practice the eigenvalues falls off very sharply like this, the last eigenvalues, the sum of these very small eigenvalues do not add up much. So we may be able to cut off at a decent value R. The R is decided by the amount of the ratio of the sum of the first R eigenvalues to the total sum of all the eigenvalues. So if I can explain 90% of the variance, if I can explain 95% of the variance, the R will vary between 90 or 91, 95 or 99. So that is something you start with, the level of approximation you are willing to accept to start with. So given that, I can define, so you decide the number of percentage you are comfortable with. Based on that I can fix the value of R. Once I have the value of R, then I can pick the first R eigenvalues and consider an eigen approximation to A. So A can be approximated by product of two rank R matrices. So that's which is called reduced rank approximation to the square root. A reduced rank approximation obtained by appropriately selecting the columns that go into the definition of the square root matrix. Now we are so that is one way to be able to reduce the rank. Why would you reduce the rank? If the computation of the full rank becomes too difficult, too expensive, we may settle for an approximation. The approximation could be R rank approximation. So that is one thought. So what is that we have done? We have simply explained one form of taking square roots, one form of taking reduced rank square roots. These are simply ideas by which I can deal with full rank square root or reduced rank square root. The advantage of eigenvalue decomposition based square root allows for this flexibility of being able to consider the square root of full rank or reduced rank. That's the key message of the first 4 slides of this module. Now I am going to go back to using Cholesky factor as a square root. So we are going to use Cholesky factorization. So this means we are going to be talking about full rank. So let forecast covariance at time k, I am still concerned with the Kalman filter. Please recall Kalman, we would like to be able to rewrite the Kalman filter equation in the covariance square root form. So that is simply the product of the Cholesky factor SKF and SKF transpose. Please understand the Cholesky factors A is equal to G transpose, where G is lower triangular, G transpose is upper triangular. So in this case SKF is a lower triangular square root of PKF and its transpose is SKF transpose. So this is simply a Cholesky factorization of the forecast covariance. Likewise I have the analysis covariance, its square root. So we are going to rewrite the Kalman filter equation instead of PKF using SKF. Instead of using PK hat I am going to rewrite it using SK hat. I am also trying to get a square root factor for QK, which is equal to XKQ and SKQ transpose. So in here SKF, SK hat and SKQ are all lower triangular matrices, and it is lower triangular matrix times its transpose. Now let us try to consider the forecast of the covariance matrix under the Kalman filter derivation that we already have done. The forecast covariance at time k plus 1 depends on the analysis covariance at time k. Now replace the forecast covariance by its square root, replace the model noise covariance by its square root. So you can readily see Mk times the square root times Mk transpose plus the product of the two Cholesky factors, the lower triangular upper triangular part of Qk plus 1. This can be rewritten in the matrix form as Mk Sk hat plus Xk plus 1 Q and the transpose of that. So you can readily see that the product this equal to this product and that product is equal to that. Now I am going to concoct a new matrix which is Xk plus 1 bar F, which is given by this matrix. So this matrix according to this is Xk plus 1, therefore Pk plus 1 has this form of Cholesky factor. So what does this tell you? This essentially tells you that if I have a Cholesky factor expression for Pk hat, if I have a Cholesky expression for Qk plus 1, I can get the corresponding Cholesky factor for the forecast covariance, which is given by this equation. Each of these equations, they are all n by n, they are all n by n, they are all n by n. But however this equation that describes the covariance of the square root of the covariance of the forecast is unfortunately is a matrix of size n by 2n. N by 2n is not a square matrix, n by 2n is a rectangular matrix. It has doubled the number of columns as the rows. That is undesirable. So while we are interested in keeping the square root, we cannot allow the expansion for the size of the matrices. Here the expansion for the size of the matrices essentially comes from the fact that the forecast covariance is sum of two terms, one coming from the analysis covariance, another coming from the model error or model noise covariance. So this doubling of the column increases the storage as well as time. We cannot allow this to happen, so we have to reduce it back to n by n matrix. Computationally it is required to reduce n by n matrices. Therefore when we try to reduce an n by 2n matrix to n by n matrix, we have to take care of the fact that we don't lose any information. So this must be information lossless transformation while I am trying to compress the number of columns from 2n to n. That's the goal. This can be done very easily by the method that we already know, that's called Gram-Schmidt orthogonalization process, which we saw in the context of QR decomposition. So what is the basic idea? If Q in this case, because my xk bar, please understand, my xk bar fk plus 1, my xk bar xk plus 1 is a matrix of size n by 2n. The corresponding Q I would like to be able to be of the size 2n by n with orthogonal columns, and the property Q transpose Q is the Q transpose Q is I. Q transpose Q is I. That is the condition we need. That means, let us look at this now. Sk plus 1 f bar belongs to Rn by 2n. So therefore S bar k plus 1 f transpose is a 2n by n matrix. This matrix has more columns than rows. So this matrix it looks like, so this essentially corresponds to the overdetermined case of H that we have used in the context of static inverse problems. So this matrix is a rectangular matrix with double the number of rows than the number of columns. Q is a matrix again 2n by n. I would like to be able to now get a matrix xk plus 1 f. So here what is the condition? I would like to get a matrix xk plus 1 f that is also n by n. So the left hand side is given. I have to find a Q and a sk plus 1 such that this equation can be satisfied. That is a classical QR decomposition method. That is a classical QR decomposition method. QR decomposition method by applying to this matrix x k plus 1 bar f transpose. So I am going to apply the QR decomposition to this. The QR decomposition will then deliver a Q and an xk plus 1. I am sorry, there is no bar here. Sk plus 1, that it will deliver an xk plus 1 f. This will be an n by n matrix. This will be a 2n by n matrix. So with these two, now you can readily see I'm trying to move towards reducing an n by 2n matrix to an n by n matrix. To see that, what is that we would like to do? We would like to be able to consider the old expression for pk plus 1 f, which is equal to xk plus 1 bar f times its transpose. This comes from the previous slide. Now I have expressed the xk plus 1 f using the QR decomposition. Q transpose Q is I, therefore it reduces to this. So you can now readily see by using the trick of QR decomposition on the expanded matrices, I can now compress the matrix back to n by n. So this is an additional step I have to do if I want to keep track of the full rank. So here comes some of the challenges in Kalman filter equation when you want to rewrite from the covariance form to the covariance square root form. Again, I would like to remind you, why do we go from covariance to covariance square root form? Simply because I would like to be able to increase the conditioning. And what is the conditioning? The conditioning for a square root is much better than the condition for the original matrix. That is a very well known result. That is a very well known result. Why is that? So we have expressed pk plus 1 in terms of square root of 2n by n matrices. So with this we come back to rewriting the filter in terms of square root matrices, given now xk bar xk hat sk hat, sk plus 1 q, these are the two square roots of the analysis and the model noise. I am going to now consider the forecast step. This is the forecast. So instead of updating the forecast covariance, I am going to update the square root of the forecast covariance. The square root of the forecast covariance is related to analysis and we have already broken them down. Therefore xk plus 1 f is equal to xk plus 1 bar q transpose, that is given by this times that, and this product is going to give us the required Cholesky decomposition as we have seen in the previous slide. The data assimilation step now consists of the Kalman gain. The data assimilation step consists of the Kalman gain. It is the forecast covariance. The Kalman gain can be written in the square root using the square root forms. Now I am going to change the matrices hk xk, the product that comes in here, I am going to call it A. So this I can rewrite also as A transpose times A using the same notation and using the same factorization for pk plus 1. Therefore kk now gets this form, and this form is the square root version of the Kalman gain. So we have come to a square root version of the Kalman gain, and I can now substitute in the analysis covariance. This is the analysis covariance form. Again I can substitute, simplify this like this. Now I can express this in the square root form, I can express this in the square root form. I already have a square root form expression for kk plus 1 in the previous slide. By combining them all I get the square root form for the analysis covariance. So to complete the square root version, I simply need to be able to compute the square root of the term which is in the bracket. So I would like to be able to get the square root algorithm to factorize the n by n matrix inside the square bracket. In order to be able to do that, look at this now. I minus A times A transpose A plus RK inverse A transpose, that is the matrix whose square root I am interested in. This has to be done in a couple of stages. First compute B as a solution of A transpose A R plus RK plus 1. Please understand, the B will then give us A transpose A plus RK plus 1 inverse A transpose. If you go back to the previous step, that is the expression which is one of the parts of the part of the equation that I already have. So this is the part that we are now concerned with, and that is computed by solving a linear system. This linear system is solved again by use of Cholesky. Please understand, even though I need the inverse, even though the expression uses the inverse, I do not want the inverse, I want the product. The product is simply the solution of A transpose A plus RK plus 1 times B is equal to A transpose. You simply solving the system of linear equations to get this. So once you get B, the term, going back to the previous slide, pk plus 1 is equal to xk plus 1, the term within parenthesis sk plus 1 f transpose. So I need to be able to find the square root of the term within the parenthesis, and in order to find the square root of the term within the parenthesis, once I find B, I need to be able to find the square root of I minus AB. I minus AB, so I know what A is, I now know what B is, multiply AB, subtract from I, and then find the square root. This square root also can be applied by using Cholesky factorization. Substituting all this back, I have xk plus 1 cc transpose this. I am now going to define xk plus 1 hat times xk plus 1 hat transpose, where sk plus 1 hat is equal to sk plus 1 f times c. So this is one of the fundamental equations in the square root operations. To find c, so the key is to find c. To find c, I have to do a factorization here, and to find b, I have to solve a linear system. So by doing steps 1, 2 and 3, I can find c. So c, what does it do? It essentially transforms the forecast square root covariance matrix to the analysis square root covariance. So from forecast to analysis, from forecast to analysis, the transformation is obtained by multiplying the forecast square root by c on the right, where c is obtained by solution of 1 and 2. So with this, I have now come to the summary of the square root algorithm, square root version of the classical Kalman filter equation. The model equation is given by this, observation is given by that, the forecast is given by classical Kalman filter. I am assuming I am available, I have availability square root of the analysis. I am also assuming the availability of square root of the model noise. Q is available from the QR decomposition, which is the Gram-Schmidt orthogonalization. So by doing a Gram-Schmidt orthogonalization on this matrix, I get sk plus 1 f. Please remember Q transpose Q is I. Now I am going to go to the data assimilation step. The data assimilation step essentially the same as the previous one, except that I am going to express kk in the square root version, where please remember ak is given by this, and xk plus 1 hat is equal to xk plus 1 f times c, where c is equal to I minus ab and b is equal to A transpose A plus RK plus 1 whole inverse times A transpose. So this essentially gives you the forecast part, this essentially gives the analysis part. This step takes care of the square root, this step takes care of the square root, this step also takes care of the square root. So this is the summary of the square root version of the Kalman filter equation. You can see there are lots of mathematical ideas, but everything rests on the ability to be able to compute the square root of a covariance matrix. So, and transformations that are needed to compress the expansion. So by combining the square root and the ability to do a QR decomposition, I can in fact derive the square root version of the Kalman filter. It was this kind of a square root version of the Kalman filter that was implemented in the Apollo mission that led to a very successful ability to track, and that was one of the major applications of the Kalman filter equations in space exploration. So given that as a background, now I am going to talk about what is called Potter's algorithm. Potter's algorithm is further simplification of the application of the square root version of the Kalman filter equation. To be able to illustrate the Potter's algorithm, I am going to assume m is 1. That means observation, I have only one single scalar observation. So hk is the state is still n by n vector. So z is equal to h times x. This is a scalar, this is 1 by 1, therefore this is 1 by n times n by 1. Rk, this is r sub k, which is the variance of the scalar observation is r. So the forecast step is the same. the forecast step is the same as the general equation that we have given in the previous slide. Now I would like to be able to look at the simplification that results when m is 1 in the analysis step. So hk plus 1 pk plus 1 hk plus 1 is equal to this, that is a scalar. So A, which is given by hk plus 1 sk plus 1 f transpose, this is equal to h times that is simply a column vector. So A is a column vector, so A transpose A is a scalar, R is a scalar, so alpha is a scalar, alpha is given by this. So A transpose A plus R is 1 over alpha, therefore A transpose A is equal to 1 over alpha minus R, which is equal to given by this. Therefore I can write the Kalman gain in this particular case as kk plus 1 is equal to alpha times sk plus 1 A, which is again a column vector. So the covariance matrix, analysis covariance matrix, can be written like this. Now please realize xk plus 1 f times 1 minus alpha times AA transpose. I'm sorry, this is not 1, it's identity times AA transpose. This is identity times AA transpose. So in this particular case, the A is a column vector, A transpose is a row vector, so this is an outer product matrix. Alpha is a constant, so I minus constant times a matrix times this. So this is the expression for the forecast covariance. Analysis covariance at time k plus 1. Please remember, I'm talking about the data assimilation step, compute the Kalman gain and the analysis covariance in here. Now if I want to be able to, so this is this factor in this case is already a square root form, this factor is already a square root form. So to get a square root I need to consider square root of only the term within the parenthesis. The analysis is very similar to the general case we talked about. So the square root of this matrix I minus alpha times AA transpose is equal to, I would like to be able to express it as a square of the matrix with a change in constant beta. If I would like to be able to make this equal to the square of this matrix, I have the relation, this relation that essentially helps us to be able to find beta. Let's go back and remind ourselves all the A is a column vector. So AA transpose is a rank 1 matrix. So that's what we are now trying to talk about. So this relation essentially implies I minus alpha times A transpose is equal to 1 minus 2 beta A transpose plus beta square A transpose A transpose because of the square involved. So I would like to be able to find a relation between alpha and beta, and that essentially tells, so by equating these two, by equating these two, I would like to be able to express beta in terms of alpha, and that gives rise to the relation that alpha and beta must be related to this, alpha and beta must be related to that. Look at alpha and beta related to that. In other words, I am going to equate both sides, the corresponding terms. So minus alpha must be equal to minus 2 beta times beta square times A transpose A. A transpose A is a scalar. So this term can be written succinctly as beta square A transpose A times AA transpose. So AA transpose is the term that I am equating. There is a AA transpose here, there is a AA transpose here. So if I consider the coefficients and equate the coefficients of AA transpose terms on both sides, I get this equality. That equality implies that beta and alpha must stand in relation, which is the equation, which is related by that equation. Now please understand, A transpose A is a scalar. A transpose A is a scalar. Therefore, this becomes a quadratic equation in beta. This is the quadratic equation in beta. The solution for the quadratic equation is given by this. So if I substitute back and unwind all the expressions, I get beta is given by this expression. I can now substitute the matrix within this as I minus beta times AA transpose square, because I have found the square root of that. That essentially gives you the analysis square root is the forecast square root multiplied by this, and this plays the role of the C matrix that we have talked about in the previous slides. That's the transformation. Therefore, Sk plus 1 is equal to a Pk plus 1 hat is equal to Xk plus 1 hat times Xk plus 1 hat Sk plus 1 hat transpose. Therefore, this is the forecast. This is the analysis covariance. Analysis covariance square root. So we have now a very simple factorization scheme when there is only one scalar observation. I don't have to take a matrix square root. Matrix square root is more expensive than scalar valued square root operations. So that's the advantage of considering when m is equal to 1. How do we apply this m is equal to 1 to a general case? In general case, my observation is a m vector is given by this. Now I am going to consider my V. The covariance of V is R. R can be expressed as a product of L and a transpose. That is a Cholesky decomposition. If you multiply both sides by L inverse, I get a new equation for the observation. So this becomes the new equation for the observation. And what is the point of this observation? The covariance of V bar, this must be V bar. The covariance of V bar is equal to expected value of V bar transpose. That is equal to L inverse covariance of V times L, that is equal to I. So what does this mean? This essentially means the noise covariance is identity. If noise covariance is identity, so what is that we have? Z bar is equal to H bar X plus V bar. V bar is a normal noise vector with 0 mean, and I as the identity matrix as the covariance. Therefore, there is no correlation between Zi and Z, no correlation between Z bar I and Z bar J, and I not equal to J, when I not equal to J. Because these things are not correlated, now I could consider Z bar 1, Z bar 2 and Z bar M, that is Z bar is equal to that, and I could consider now each of these observations as a single observation. So there are m single observations. I can try to successively assimilate each of these observations by the Potter's algorithm that we have given in the previous case. Therefore, instead of assimilating all of them together, that involves matrix operations, I can by doing this transformation try to convert the problem into one of assimilating m scalar observations. So it is this ability to convert using the transformation which is the L inverse, is called whitening transformation. What is whitening? Before the transformation, V had covariances. That means Vi and Vj may be correlated. But after the transformation, V bar I and V bar j are not correlated. So in here, please realize, in here the V bar is equal to V bar I, I'm sorry, V bar 1, V bar 2, all the way up to V bar m, and if you take any two of them, they are not correlated. Therefore, I can consider the vector to be made up of m single uncorrelated observation. If there are m single uncorrelated observation, I can apply the Potter's formula one at a time. So I start with the forecast, you assimilate the first component, you get an analysis. Then start with that analysis, assimilate the second component, then you get another analysis. You start with that second analysis, assimilate the third observation, you get the third analysis. Likewise, if you assimilate all the m components one at a time, starting from a forecast in m steps, you will get the ultimate analysis that takes advantage of all the m individual observations that are arising out of whitening transformation. So this way one can bring in simplicity into the computation by using suitable transformations. Now we have talked about several different types of transformation in this lecture. In this lecture we have talked about square root transformation of matrices, QR decomposition to be able to reduce or compress in a lossless way the resulting square roots. And here we are also talking about the notion of Potter's algorithm and how to apply Potter's algorithm component wise by doing what is called a whitening transformation or a whitening filter. What is a whitening filter? If I pass a correlated noise through a whitening filter, the output becomes uncorrelated in the sense that V was correlated, V bar, the components of V bar are uncorrelated. This ability to transform a noise vector that is a correlated covariance matrix to an uncorrelated covariance matrix and the output, that is called the whitening filter. By applying the whitening filter, we are able to reduce the problem of assimilating a vector of m observation to assimilating a sequence of scalar updates of m single observations. So the assimilation step is broken down into m simple steps where you simply take the square roots of scalars as opposed to taking square roots of matrices. The total time required to compute the square roots of matrices can be much larger. Therefore, if you could apply Potter's algorithm, it could greatly simplify the analysis. Not only that, it also improves the conditioning of the conditioning of the matrices, which in turn tries to induce the stability of the computations. With that, we come to the end of the discussion of this covariance square root filter. This is covered in chapter 28 of our book, and there are enough number of exercises one has to perform in trying to verify all these things. That is why I have not given you any additional exercises. Trying to verify all the calculations in here are themselves an exercise. I hope you have come to appreciate the notion of what type of square root to use. Do I use full rank approximation or partial rank approximation? If I were to do a square root version of the covariance, how these transformations are aligned. Then if I want to be able to incorporate one observation at a time, how Potter's algorithm come to the rescue. So by use of whitening transformation and Potter's algorithm, we can further simplify the assimilation of vector observations. So that is the overall summary of this module. Thank you very much.